Good day, Met 330 students. In this video, we're going to talk about doing thermodynamic calculations using the MetPy module. And so the first thing we need to do is let's go ahead and copy some things from some previous lecture material. And so I'm going back to my SKU-T plotting lecture. And what I want to copy over are all the modules that I'm going to need. Copy and paste that into one cell. And then to get access to some sounding data so we can do some calculations. And so copy and pasting this second cell. But I need to make one addition to the modules that we're importing. And so we want to import MetPy calculation module, so metpy.calc, as mpcalc. That's going to allow us to gain access to all of the different calculations available in MetPy. Probably don't need the plots, but we'll just keep that in there for now anyway. So now we've got all of our modules imported. Let's go ahead and grab some data. And great. So we've got at least our data and modules imported to then start this idea of thinking about thermodynamic calculations, or really just calculations in general from MetPy. So we're going to go ahead and go to the MetPy calculation documentation page. And so what happens to be at the top here are our dry thermodynamic variables. And we see that there are a whole bunch of different things you can calculate in MetPy that are related to dry thermodynamics. Most of these dry thermodynamics you could also use with gridded data, which we'll do in a future lecture. There are also a whole bunch of moist calculations. Some of these are readily used for a grid, but some of these will be for primarily sounding-based point data. And then you can scroll down, you can see ones that are for soundings in particular, which are things related to things like parcel profiles and CAPE and SYN and all those types of things. Then as we get down here to dynamic and kinematic, some of these are more for your grid stuff. We got some turbulence calculations, other mathematical functions, some apparent temperature, and then just other categories. And so there's a lot of different things that you can use within this module to help do some calculations. And so one of the first ones that we want to do is actually potential temperature. So let's go ahead and click on the potential temperature to learn a little bit about this equation. And so here, the name of the function is potential underscore temperature. Its input parameters are pressure as a pint quantity and temperature as a pint quantity. Hence why we want to get all of our variables that we read in with units attached. And then what it's going to return is the potential temperature as a pint quantity. And it's going to use this following equation. Theta equals T times P naught over P to the kappa. And kappa here is our RD over C sub P. And so here's an example of doing just a simple calculation based on an 800 millibar temperature value of 273, which would equal 290.966 Kelvin. So let's go ahead and see how this works. Let's go back to our Jupyter lab here. And I've got a little error in my equation here, so we're going to go ahead and quickly rectify that. Make that our P naught, our P. Our P naught is typically taken to be 1,000 millibars. Our RD over C sub P there is our 287 over 1,004. And then temperature, obviously, in Kelvin. And so we've got all of this data read in from our sounding from January 11th, 2005 from Norman, Oklahoma. So how do we call this potential temperature equation? Well, remember we brought in our calculation module as mpcalc. So that's the handle. So we're going to need to call mpcalc dot and then potential underscore temperature. And then from here, we need to feed it our proper values. And so it's pressure and then temperature. And so this order matters very much, right? And so our pressure variable is P, and our temperature variable is T. And so as long as we have the same number of pressures as we have temperatures, we can feed an array right into this function, such that when we run that, it calculates our theta really, really quickly. And then we can look at the output and see that we now have our theta values, our potential temperature values calculated for each level. And so you might recall from a previous video, this first value, it was at a pressure of 971, so it only had to come back down to 1,000 millibars, so it's probably just slightly higher than the actual temperature, versus values up at 100 millibars being 409 Kelvin when you bring them back diabatically all the way to the surface. So it's not too hard to do and use some of these equations. And again, here we see that we have units that are brought out. Again, we could strip the units if need be, using .m or .magnitude. But let's go ahead and look at maybe a slightly more complicated function from MetPy, one that calculates the parcel profile or the parcel path. And so what I've done here is I've grabbed the information from the documentation page, but we could also find that on the documentation page if we click back. And it'll be under moist thermodynamics, right? Because to lift a parcel, we initially lift dry adiabatically until saturation and then moist adiabatically. Actually it's under our sounding, and so our parcel underscore profile is where we have our information about our parcel profile. And you can see that it links a couple of examples that calculate or use parcel profile in those examples. And so what we see here is we have input parameters of pressure, the starting temperature, and the starting dew points. And actually I believe these parameters have now been updated a little bit, or will be, that dew PT will probably be dew point in the future. Doesn't matter for our end here, because we know our dew point, and so we need to feed it all the pressures, right? Because we need to figure out the temperature of our parcel at each pressure level in order to do our plotting well. And so again, we call MP calc, and then it's parcel underscore profile. Oops, if I could type parcel, not partle, parcel. And then again, we see that pressure, temperature, dew points. And so our pressure is P, but then we need just the starting temperature. And so we have our T variable, which is all of our temperatures, but what's the first one? How do we get the first out of a one-dimensional array? How do we get that first element? That's right, square bracket 0 gives us just that first element. And same thing for our dew point. So what we're essentially doing here is we are doing a surface-based parcel that's being lifted according to the appropriate things for our parcel path. And that we're saving it off in this parameter called profile. So let's go ahead and run that. And so it runs pretty quickly. And we can look at prof. And so now these are the temperatures in Kelvin for our parcel profile. Now the question is, when we're plotting our SQT, what units have we been using to plot? That's right, Celsius. And so we can actually convert this to Celsius. We could either convert this prof and save it off to a new variable name, or by adding some parentheses. That means that this calculation is going to happen first with parcel profile. Then we can say to deg C to then have it change the temperature variable from Kelvin to deg C. And then if we look at profile, now we are in our degrees Celsius, which will be easier for plotting purposes. So that's it. So calculations are pretty easy. You just have to learn what goes into the input here. And so, for example, in this parcel profile, it's all the pressures because we want to get the parcel temperature at each of the pressure levels that are in our sounding data, given just the starting temperature and starting dew point. There are more complicated parcels that you can do. You can do mixed layer parcels and stuff like that, and there are functions to help you out in MetPy. But let's go ahead and see what this parcel profile looks like when we plot. So let's go back to our CUT plotting. Let's scroll down and get our nice, more complicated, more beautiful looking CUT plot. We're going to copy and paste. I'm going to go ahead and get rid of this text stuff because I don't want to plot that this time. And let's go ahead and just rerun this to make sure we get a plot first. Sure enough, we get our nice plot from January 11th, 2005 at 12 UTC. But let's go ahead and plot the parcel profile here. So the question is, how do we plot the parcel profile? We again use skew.plot. And again, we are still in this pressure, comma, temperature format. And so our pressure is still our p-values. But now we want to plot the parcel temperatures. And our parcel temperatures is what we just calculated up here with our parcel profile, which we saved off as the variable name prof, short for profile. And so we can type prof, and we could change the color to black. And so we do that. We see that since we're nearly saturated or absolutely saturated at the surface, we immediately go up moist adiabatically and kind of follow those green dashed moist adiabat lines. And so this isn't maybe the best profile to check with a parcel profile to see what it does. So let's go ahead and change our data. So let's scroll all the way back up to the top here, and let's just change to a different day. So let's say 2004. Let's go 6, 12, and let's change to ICT, Wichita. Doesn't believe that Wichita is a station. So let's go ahead and look that up. Let's go to the Wyoming site. Wyoming Sounding Archive. Click on here. We can look on the map. We see, okay, we have Dodge City, Topeka. Oh, let's do SGF. That's closer to Wichita. So change this to SGF. Get our data from June 12th, 2004. We can recalculate our theta if we wanted to. Didn't really need to do that. Let's recalculate our profile. Much different profile in this case. And then 12 UTC 12 June 2004. Actually, this is where we would maybe want to use an F string with our date function to help us out so we didn't have to manually recreate this date in our profile. But then if we go ahead and run our sounding, we see a much different sounding where we have a small dry adiabatic ascent before our moist adiabatic ascent. And we could then analyze things like CAPE and SYN associated with this profile, at least in a graphical sense, or using MetPy in a numeric sense, as we do have the ability to calculate CAPE. And so it's pretty easy to use calculations, especially for soundings. And so the hardest thing, though, is getting in there and digging in and figuring out how to use them. And that's something that you kind of have to struggle with so that then you can utilize these skill sets for new functions that may be developed in the future, or for functions that go beyond what we're doing for this particular unit. So that's it for this video. Hope you enjoyed it. Thanks for watching.